We have used the V8 tick processor to read raw profiling data. Now let's talk about a far more powerful and visually intuitive way to understand CPU behavior: flame graphs. A flame graph is a visualization technique invented by Brendan Gregg, an engineer at Netflix who became one of the world's foremost experts on performance analysis. The idea is to take call stack samples, exactly the kind of data the V8 profiler and Linux perf tool collect, and render them as a stacked bar chart where each bar represents a function call. Here is how to read a flame graph. The x-axis represents time, but not in strict left-to-right chronological order. Instead, the width of each block represents how frequently that function appeared in samples. Wider means it was sampled more often, meaning it used more CPU time. The y-axis is the call stack. The bottom of the graph is always the root, the process entry point, like node or main. As you go up, each level represents a function that was called by the one below it. So if a function was called by another function, the first function appears on top of the second. The higher up the stack, the closer to the actual work being done. And because the top of a flame tapers, caller functions are always at least as wide as their calls, the graph literally looks like flames. The colors are worn by convention: reds, oranges, and yellows. This is not semantic, the color itself does not tell you severity. The width tells you severity. A wide, tall flame is a hot path consuming significant CPU. A narrow spike, no matter how tall, means the stack depth is large but the duration is short. Flame graphs can visualize more than just CPU time. You can generate off-CPU flame graphs to see where your application is blocked waiting for I/O, shown in cool colors like blue and green. A mix of on-CPU and off-CPU flame graphs together gives you the most complete picture of how your application spends its time. Wide hot flames mean your CPU is under heavy load from that code path. Tall thin spikes mean deep call chains with low duration, normal for event-driven Node.js applications. Let's walk through the actual process of generating a flame graph for your Node.js application on Linux. This requires a few tools, but the process is straightforward. First, install the Linux performance tools. You need the perf command, which comes from the Linux tools package. On Ubuntu or Debian, $sudo apt-get update $sudo apt-get install Linux tools. Common Linux tools 6.8.0-124 generic. The name or substitution ensures you get the kernel version match tools package. Next, start your Node.js server with two important flags. First, perf basic prof, which tells V8 to write a perf map file that maps memory addresses to JavaScript function names. Without this, perf will record addresses but not function names, and your flame graph will be full of anonymous memory locations. Second, run it in the background with ampersand so you can see its PID. $node perf basic prof fib.js ind 1-30462 capture that PID 30462 in this example. Now run perf to record call stack samples for 60 seconds at 99 Hz. $perf record F99P30462G sleep 60. Breaking down these flags, F99 means sample at 99 Hz, 99 times per second, not 100, to avoid harmonics with other periodic tasks. P30462 targets our Node.js process. G enables call graph recording. Without this you only get flat samples, not stack traces. Sleep 60 means run perf for 60 seconds. While perf is running, in a second terminal, run your benchmark load, $aben 1000 http //localhost 3000 once perf finishes, you have a perf.data file. Extract the stack trace, $perf script stack01.trace. Now clone Brendan Gregg's flamegraph repository, which provides the Perl scripts to convert stack traces into SVG flame graphs. $git clone depth 1 http://github.com/brendangreg/flamegraph $flamegraph/stack collapse perf.pl stack01.trace. /flamegraph/flamegraph.pl stack01.svg open stack01.svg in your browser. It is interactive. You can click on any block to zoom into that region of the call stack, and click the lowest block to reset zoom. This interactivity is what makes flame graphs so powerful for deep dive investigations. Flame graphs with perf are powerful, but they are Linux specific. Let's cover the full landscape of profiling alternatives so you know your options on different platforms and for different use cases. Dtrace is a dynamic tracing framework originally developed at Sun Microsystems and available on Illumos-based systems, SmartOS, OmniOS, macOS, and BSD variants. It is extremely powerful. You can trace kernel events, user space function calls, and system calls all in one tool. Brendan Gregg's flame graph tooling originally used dtrace output. On Node.js, dtrace support has been available for some time, but the book notes that on Linux specifically, dtrace is not the recommended path. Linux's perf is more readily available and better supported for the kernel version you are likely running. The Node Inspector tool provides CPU profiles through the Chrome DevTools interface. You start your application with Node Inspector, open Chrome, connect to the debugging interface, and click Record CPU Profile. This gives you a profile in the Chrome Profiler tab, a tree view and a flame chart rendered right in the browser. This approach is more accessible than raw perf data and is a good starting point for developers who are not comfortable with command-line profiling tools. However, note that Node Inspector instruments JavaScript-level execution and may not capture the full picture of kernel and I/O time the way perf does. The book's strong recommendation: prefer operating system-level profiling tools over language-level ones. OS-level tools like perf and dtrace are faster, less intrusive, and give you a bigger picture. They show you not just your JavaScript code, but also the Node.js internals, the lib of thread pool activity, and kernel calls. Language-level profiling only shows you what is happening inside V8. Flame graphs are also not limited to CPU time. You can trace device I/O calls and syscalls. You can filter to specific function calls to see when and for how long a function is used. You can trace memory allocations and even capture allocation sizes in bytes instead of call frequency. This versatility makes flame graphs one of the most broadly useful tools in a Node.js performance engineer's toolkit. As a final rule of thumb from the book, a wide, fat flame means your CPU is being exhausted. High but thin flames mean your call stacks are deep but short-lived, which is the normal healthy pattern for event-driven, asynchronous Node.js applications.